Happy Wednesday to everyone. We'd like to take a look at chapter 9 today. So the last time that we got together, we finished up chapter 8, looking at section 8.3. And again, today we would like to begin taking a look at chapter 9. A quick comment about how things are going along. I'm a little bit behind on some grading, so we have grades for our second exam have not been determined yet, so I still need to grade those. The plan is to have those graded by the end of this week or over the weekend, and then those grades should be posted sometime next week. Once those grades are posted, I'll try to update everything on Blackboard, look at your most current grade, homework grade on my stat lab, bring that into Blackboard and get all of the grades updated in Blackboard. So that's where I'm at with that. All right, so let's see, what else was there? Yes, okay. On Friday, I am going to talk about section 9.2. So today we're going to talk about section 9.1. On Friday, we'll take a look at 9.2. According to the schedule, we were only hoping to talk about through 9.1 this week, but we actually don't have section 9.4 anywhere on the schedule. So having the opportunity to cover 9.2 on Friday will allow us to talk about section 9.4 next week. So that way we stay on track. So that will be good. But one step further, I'm actually going to post a video. So I'm pre-recording our lecture for Friday, and I'm going to post a video for that lecture. Now, I think what I might do is I might just use a video that I recorded from the spring semester. So the notes are the same, but I did make some minor adjustments to the slides. So it might not match absolutely perfectly, but it will be more than sufficient. It's exactly the same content. So it's still section 9.2, of course. So 9.2 on Friday, and if you show up in Zoom, you'll probably find that I'm either not here or that I'm here and I'm telling you to go watch the video that will be posted. I would post it right now, but unfortunately, I don't have that video on this computer. It's on a different computer, so I'll have to post it either later today or tomorrow, or maybe even Friday morning. Just watch for the link. It will be posted in the usual place. So it would just follow today's lecture. All right, so let's go ahead and get started. So we want to talk about chapter 9. So chapter 9 is all about hypothesis tests, which is fantastic, right? We've been talking a little bit about hypothesis tests. Not the idea of what they are or even how to do them, but we've said that they play a role in our statistical project for the semester. So we are finally getting to this idea. Once we're through chapter 9, we should be pretty much all set and not have any concerns about what exactly our proposal should look like or our project. Right? We should have a pretty complete picture by the end of chapter 9. Which we should finish up not quite next week, but the beginning of the following week, I believe. So let's see here. All right, hypothesis tests for one population mean. There are ways that we can compare two population means, but for now we're trying to keep things simple with just hypothesis tests for one population mean. So we'll start off with a really basic introduction of what is hypothesis testing, what are we looking for, a little bit about what we're doing, and then we'll start getting into the details of it. So 9.1 is just what is this? What are we doing? What's going on here? Section 9.2 and 9.3 they give some details about the methods, but they don't actually have us perform any hypothesis tests. And then in sections 9.4 and 9.5, that's where we actually say, all right, the details that we learned in 9.2 and 9.3, this is how those details play out in the actual hypothesis tests. So 9.4 and 9.5 are actually performing hypothesis tests about a population mean. Excuse me. So we work our way up to that. 9.1, what is it? 9.2, 9.3, some details. By what method can we perform a hypothesis test? And then 9.4, 9.5, actually performing hypothesis tests. All right. So what is a hypothesis test used for? Well, essentially, it's just a way to make a decision. And in a case where we're talking about population means, right, we're simply trying to ask, or we're trying to answer one of three very basic questions. Is a mean actually equal to a specified value? Is it higher than a specified value? Or is it lower than a specified value? So these are essentially what we can answer, right? It's decision making. What are the decisions we can make? Well, how does a population mean compare to a suspected or proposed value? So it's called a hypothesis test because we create two hypotheses. We have first the null hypothesis, which is a statement about equality. We want to say the null hypothesis is that the mean is equal to something. All right. Alternatively, we want to maybe conclude that the mean is higher or lower or not equal to. So the alternative hypothesis is if it's not the null one, if it's not the first one, then we're saying it is this other one. So our tests look at the null hypothesis. Is the null hypothesis true according to the data that we found? Yes or no. And then we move on to if no, then it's the alternative. If yes, then we accept this null hypothesis. And then, of course, the hypothesis test is deciding which hypothesis to accept as the one we like. Okay. So it turns out to be they have some very particular language that we use, and so we'll see what that looks like later, I believe, in this section. But when we're performing a hypothesis test, it really amounts to rejecting or not rejecting the null hypothesis. So every single time, the null hypothesis is the same. The null hypothesis is that the population mean is equal to some particular value. So we might be talking about the mean height of CUAA students, right? They tend to be relatively tall, so maybe the average height is taller than the average for everywhere else. And so you might say it's 73 inches. Mu is 73 inches. Excellent. So you might take a look at something like that, and then alternatively, well, are we really any different from other places? So maybe the population mean everywhere else is actually smaller than that. So we're saying it's 73, but is it really actually closer to what everyone else is? So we might say the alternative. So this would be our null. An alternative might be that in reality we're not that much taller than everyone else, and so it's less than 73 inches. Okay, so we might see something like that. That's right. We talk about a population mean. We're saying it is equal to something, and we either want to say it is less than, it's greater than, or not equal to. So in particular right here, I could not find the appropriate notation for not equal to. So this is appropriate notation for not equal to. However, when you're writing it by hand, you would simply put a line through the equal sign. So not equal and not equal. This and that mean the same thing. So make sure you're aware of that notation. When we're not working with our slides, you should see this notation. So in a textbook, they use the usual notation, and in the exam, when that time comes, the usual notation will also be used. Excellent. So again, there are three alternatives, right? There's only one null hypothesis that we consider, and three alternatives. The mean is not equal to what we said it was, the mean is less than what we said it was, or the mean is greater than what we said it was. And these will give us three different types of tests. And they each have a name, so we approach them each ever so slightly differently. They're all pretty much the same, but the first one would be called a two-tailed test. And we'll get into the reasons behind these names as we take a look at section 9.2 and 9.3. So this is a two-tailed test. The second one is a right-tailed test. Oh, I'm sorry, that's a left-tailed test. Left-tailed test. And then a right-tailed test. And we can remember which name goes with which test, right? Which alternative hypothesis by looking at directions. Our inequality here, as long as we have mean is less than the proposed number, right? This is an arrow pointing to the left, so it is a left-tailed test. This is an arrow pointing to the right, so it is a right-tailed test. And then the only one left is a two-tailed test. We'll look at more intuitive ways of recognizing which test goes by which name later. In this case, it's just an easy way to remember based on the notation that's used. All right, so this is they call it the basic logic, but this is the wrong place here. Super basic logic of a hypothesis test. The super basic logic is that we have a null hypothesis, right? We say the mean is equal to something. We collect some data, and either the data agrees with that or it doesn't. That's it. That is the super basic logic of a hypothesis test. Many aspects of the rest of the test would, of course, be considered logical as well, but logical only with once you have an understanding of what's going on. So our goal is to make all of this seem like logic and logic and decision-making skills. So basic logic is we make a statement and then we take a sample to find out whether that sample supports or does not support our statement. So we want to take a brief look at some tests that we could do. So some statements are being made in each case. And for each of these cases, we want to give the null hypothesis, give the alternative hypothesis, and then determine if the hypothesis test is left-tailed, right-tailed, or two-tailed. So we can do this quite easily. So we've got three different situations that we want to take a look at. So we're referring back to the same situation that we were looking at in chapter 8, where Eric was throwing a frisbee. And we'll continue to take a look at this example throughout chapter 9. All right. So a hypothesis test is to be performed. All right. And we want to determine if Eric can throw a frisbee on average more than 32 yards. So we want to identify the null hypothesis, the alternative hypothesis, and then determine if it's left-tailed, right-tailed, or two-tailed. So for our null hypothesis, that's H sub 0, we want to make a statement about the mean. And we say that the mean is equal to something. This is always the null hypothesis. It's just this number here depends on the context of the problem. So in this case, we'd like to know if Eric can actually throw a frisbee on average more than 32 yards. So we're saying that in this case, it's equal to 32. And then the alternative, which we would like to conclude, the alternative is that the mean is actually larger than that. Determine if Eric can throw a frisbee on average more than 32 yards. And this tells us what type of test it is, left-tailed, right-tailed, or two-tailed. So since this inequality produces an arrow pointing to the right, we would say that this is right-tailed. Again, for now, it's just a justification, right? Our right-tailed is decided by a notation. This particular alternative hypothesis gives us what we'll find to be a right-tailed test. For now, that's it. In the next section, we should be able to get into some details about why it's called right-tailed or left-tailed or two-tailed. Or it'll be left for you to conclude. All right. So another situation, again, we are performing a hypothesis test, and we want to determine if the average distance Eric can throw a Frisbee is less than 34 yards. So again, we want to identify the null, alternative hypotheses, and what type of test needs to be performed, left-tailed, right-tailed, or two-tailed. So for part A, we want to, again, give the null hypothesis. So H sub 0 is always a statement about what the population mean is, right? The population mean is this, and we use the numbers from the problem, 34. Excellent. So the question, what we would like to conclude is, Eric can throw a Frisbee less than 34 yards, or determine, maybe his wife, Chelsea, isn't quite so confident in his ability to throw it 34 yards every time-ish. And she says, I don't think he can do that. So maybe she's performing this test. So the alternative is that the mean is actually less than the proposed 34 yards. So we have the null hypothesis, the alternative hypothesis, and here we can see that this inequality would create an arrow pointing to the left. So we say that it is a left-tailed test. Awesome. Give you one more moment here, right? The null hypothesis is always what the mean is equal to. The mean is equal to this. The alternative is saying, well, I'd like to conclude in this case, I'd like to know if he can actually throw it less, is it actually less than 34 yards? In the previous example, we said, right, hey, he can throw it 32 yards, but I wonder if he can actually throw it more. So our null was equal to 32 and the alternative was more than, because we wanted to know if it was more than 32 yards. So then, of course, we have one more situation and only one more test to consider. But again, for this hypothesis test, we want to determine the null hypothesis, the alternative hypothesis, and whether this is a left-tailed, right-tailed, or two-tailed hypothesis test. So we want to determine if Eric can throw a Frisbee on average 32 yards. Let's see here. I put is equal to, but I suspect we wanted to determine if the mean is equal to 34 yards. So we want to determine if Eric can throw a Frisbee on average 33 yards. So the null hypothesis is always a statement about what the population mean is equal to. So in the first case, we thought it was more than 32. In the second case, we thought it was less than 34. Well, between those two is 33, so let's see if it's equal to 33. The alternative, if it's not actually equal to 33, the alternative here would be that it's not equal to 33. Excellent. And then, of course, since it's not an arrow pointing left or right, that would lead us to conclude that it is a two-tailed test. And again, we'll actually take a look at why it's called each of these things or we should be able to observe it in the following sections. All right, so we want to talk a little bit about errors. When we're making decisions, we want to know if we're making the right decision. So a type 1 error is when we reject the null hypothesis, right? The mean is equal to something, whatever the number is. So we might, based on the sample that we collect, we might decide to reject the null hypothesis. And when we reject the null hypothesis, that means we conclude the alternative hypothesis. But if the null hypothesis was in fact true, right, we made a mistake. Making such mistakes is called a type 1 error. On the other hand, we might decide to not reject the null hypothesis. We might say that, well, the mean is equal to the number that we thought it was. But reality might be that it's bigger than, or less than, or simply not equal to. So the reality might be that the alternative hypothesis is actually what we wanted to conclude. But in particular, we didn't reject the null hypothesis when it's not true. So we concluded something that's not true, which is an error as well, of course. And that is called a type 2 error. So there's only 4 possibilities, right? You might, you can either decide to not reject the null hypothesis, or you can decide to reject the null hypothesis. Only 2 options for a decision. And in reality, it can either be true or it can be false. If it's true, if the null hypothesis is true and you didn't reject it, you made a correct decision. You said it's true when it's true, or you did not reject it when it is true. You could also have that it was false and you did reject it. Excellent, it was false and you rejected it. That's exactly what you need to do. Which leaves us with the remaining 2 options of what we said is false, but we did not reject it. That is an error. The other situation is it's true, but we did reject it, which again is an error. So type 1 and type 2 errors. So what we want to focus on is the probability of making a type 1 error. And the probability of making a type 1 error is what we call the significance level of a hypothesis test. And we'll find that this corresponds very nicely to the level of confidence when we're talking about confidence intervals. So this idea of significance level and confidence level are very similar. They're essentially the same thing, which is why we use the same notation, alpha. So compare this, well, a little bit later, we'll be able to compare this to talking about confidence intervals. So we want to know what happens, how do we minimize the probability of making a type 1 error, or what happens when we minimize it, this sort of thing. So, so the first thing to notice is the relationship between a type 1 and type 2 error. If you don't want to make a type 1 error, so the type 1 error would be rejecting the null hypothesis when it is true. Okay, go back one more. Type 1 error is we reject the null hypothesis when it's true. If we want to minimize this, what we would find is that it would become more likely that we would actually not reject it because we want to minimize the times that we reject it. So we opt to not reject more frequently. And as we do not reject more frequently, then we increase the probability of making a type 2 error. Okay, so this is the idea. If I were to consider, see if I can draw a straight line here. If I were to consider my actual population mean is right here. And let's see. If I want to find out whether my sample supports, right? Let's say our mean is equal to, our mean is equal to the proposed mean, right? We're making, we have a null hypothesis. If we wanted our sample to support that, then our sample needs to be within this 95% range of that. This we call 1 minus alpha. I suppose it's 100 times 1 minus alpha %. And this would be alpha over 2, and this would be alpha over 2. Right? This says that if we get a mean outside of this, we would reject and say, hey, you know what, this is too far to the left. I think that the mean is actually lower. If we end up with a mean over here, we say, hey, you know, this is too far to the right. I think that my sample supports that the mean is actually higher. So if we end up out here, then we would reject that the equality holds. That is a little bit more formal. This is what we'll talk about more in section 9.2. But this would actually be the example of a two-tailed test. A tail over here and a tail over here. Where these regions, we would say if our sample lands out here or out here, then we would reject because we're too far away, right? 95% of the time, we're going to be close enough to say don't reject. 5% of the time, we're going to be too far to the right or too far to the left. So in this case, significance level of 5% or 0.05. But this is the idea. And if we wanted to minimize this, right, if we wanted to make it smaller, make these bounds further to the right and further to the left, that increases the number of samples that would allow us to not reject. However, again, that would give us more chances where we're going to conclude that we do have equality when we actually don't. Okay, so increasing or decreasing the probability of a type 1 error increases the probability of a type 2 error. All right, that's what this slide is actually discussing. All right. So we want to take a look at a brief example. So a hypothesis test is to be performed to determine if air can throw a frisbee on average more than 32 yards. So this is what we looked at earlier. We said that the null hypothesis was that the mean is equal to 32. The alternative was that the mean I'll get this notation right. Null hypothesis mean is equal to 32. Alternative hypothesis mean is greater than 32. Excellent. So we said that this was a right-tailed test. So we might find that our data was too close to 32 for us to conclude differently. We might find that the data supported, you know, it was 37. So clearly that's going to be higher, this sort of thing. So what would it mean for us to make a type 1 error? Well, a type 1 error occurs when the null hypothesis is true, but we rejected it. So making a type 1 error would be the mean is 32, but the sample that we found supported that it was in fact higher than 32. So we decided to reject it. Okay. We either accept the null hypothesis or we reject the null hypothesis. So accept and reject are always in reference to the null hypothesis. So making a type 1 error is when the null hypothesis is true, that is, air can throw a frisbee on average 32 yards, but our data supported rejecting it. That is, our data suggested that the mean was more than 32. So that would be a type 1 error. A type 2 error would mean that the null hypothesis was not true. Null hypothesis is not true. However, our data had a mean that was relatively close, right? Our sample mean was relatively close to 32. And so we said, well, my data suggests that is true. So we're not going to reject it. So a type 2 error would be he can throw the frisbee more than 32 yards, but the data didn't show that, the sample didn't show that, and we did not reject it. So not true and not rejected. All right, and then a correct decision would be, right, to either conclude, right, do not reject when it is in fact true, or reject when it is not true. So a correct decision might look like the mean is 32 yards, and we decided not to reject it, so we concluded that, hey, the mean is 32 yards. Awesome. It is 32 yards, and we concluded it's 32 yards. Perfect. Or a correct decision would be, he can throw a Frisbee more than 32 yards, and we decided to reject the null hypothesis and conclude that he can throw a Frisbee more than 32 yards. Perfect. He can, and we concluded it. So that would be a correct decision in both cases. All right. So let's consider what type of error occurs here, if any error occurs. So let's say that the null hypothesis is rejected. We decide to reject it. What type of error is it if it was in fact equal to 32 yards? So when it is true, right, null hypothesis is true. When the null hypothesis is true and it is rejected, that is a type 1 error. And in the case that it is rejected and he can throw it more than 32 yards, it is rejected, and it's not true, this would be a correct decision. Excellent. So again, we are very particular about the conclusions that we make for a hypothesis test. And it's a little bit because when we take a sample, it only gives us an idea of the population, right? The sample is not the population. The sample only gives us an idea. So there are only two options when we perform a hypothesis test. And again, it's in reference to the null hypothesis. We either reject the null hypothesis, that is, the null hypothesis is rejected, or we do not reject it. Null hypothesis is not rejected. So we either reject or do not reject. So in either case, we follow that up with a statement, right? We conclude, right? So we reject or we do not reject. In the case that we reject, we conclude that there is sufficient evidence to support the alternative. So when we reject, there is sufficient evidence to support the alternative hypothesis. We don't know that the alternative hypothesis is actually true. It's just that our data supports it. And then in the second case, when we do not reject, we say that there's not sufficient evidence. We conclude the data does not provide sufficient evidence to support the alternative hypothesis. So data supports the alternative hypothesis and we reject the null hypothesis. Or data does not provide sufficient evidence to support the alternative and we do not reject the null hypothesis. Those are the only options of how a hypothesis test can end, how it concludes. But we do want to be very specific. This language, this gives us an outline, right? Very small one-sentence outlines for what our responses should look like, what our conclusions should look like at the end of every single hypothesis test. These very specifically are the conclusions to a hypothesis test. We don't conclude that the alternative is true. We never conclude that. We only conclude that this data either supports or does not support the alternative hypothesis, okay? Again, this is a sample. It's not actual population. So what is actually true, where we still cannot be 100% certain about. We could only be 100% certain when we actually find that population data. So a sample either supports or does not support an alternative hypothesis. And that's it for this section. So these are the topics that we talked about: null and alternative hypotheses, and of course the hypothesis test. Does the data support or not support? That is the basic logic of a hypothesis test. What type of errors can we make? The significance level refers to a type 1 error. The significance level is the probability of making a type 1 error. And as we decrease the probability of making a type 1 error, we increase the probability of making a type 2 error. Of specific concern to us will be the probability of making a type 1 error. And finally, there are only two possible conclusions for a hypothesis test. The null hypothesis is rejected, and we conclude that the data supports the alternative hypothesis, or we do not reject the null hypothesis, and we conclude that the data does not support the alternative hypothesis. And that's it. So make sure you take a look at the homework. Of course, the homework for section 9.2 is also not quite due next week because it wasn't supposed to be talked about until next week. So you have almost 2 weeks. You have 2 weeks actually before section 9.2 homework, or 9. Wait, no, hold on a second. 9.1 homework is due next week. 9.2, which is what we'll talk about on Friday, that's what's not due until 2 weeks from now. So 9.1 is due next week, I do believe. We could double check that. If it happens to be due later, well, that's extremely convenient, but it should not, it's of course not due today. All right. Next time we get together, we'll talk about section 9.2, the critical value approach to hypothesis testing, but I will leave that for Friday since we have plenty of time to do that. So thank you for your time and your attention today. If you have any questions, I would encourage you to stick around and ask them. But if you don't have any, again, have yourself a wonderful day.